Right, in the previous discussions, where we look at the transfer functions and transfer functions of any dynamic system, and we will actually try to work out some of the key parameters indicating, for example, for a first order, a second order system. One of the parameters we tend to look at is the DC gain. Now, DC gain gives you the response in steady state, or the output of the system in steady state after the initial transitions, to a step input or to a ramp input, that kind of input. And basically, if you have a DC gain of 1 for a system or from its transfer function, then the output will equal to input in steady state. DC gain equals to 2, then output would be twice of the input in steady state, and so on. But in this part, we're going to change the input, okay, from a step or from a ramp. We're going to look at sinusoidal inputs. Now, if you think about sinusoidal inputs, you will have amplitude, you will have different frequencies, and you're going to have some initial phase angles as well. Okay? In particular, when the frequency changes, the response will be different. Okay, so we can look at how we can work out the output response in the steady state after the initial transition period has passed. Okay, and how we can use the transfer function to do that. That's the first part of this discussion. The second part is actually we're going to look at the behavior of a system to different frequencies and try to construct some frequency response diagrams that are used quite often or commonly by control engineers to help and design controllers. So really this serves two purposes, the discussion in this part. One is to find the steady state response to sinusoidal input of different frequencies. The other is to try to construct frequency response diagrams or frequency response plots from transfer functions so that we can use them for control design. Okay, so we can look at the first issue first. Now, suppose I have a system GS, okay, and I know the transfer function, and the input is some R, okay, RS is the input in frequency domain, YS is the input output in frequency domain, but I'm really looking at the RT, that's an input in time domain. If RT is some sine wave as defined by equation number 1, so amplitude is A, that's the peak value, okay, of a sine wave. Frequency is the coefficient of T, okay, so this omega naught is the frequency of that sine wave. It determines how many cycles you get per second, okay, or how many radians per second in a second. And omega naught is actually, the unit of omega naught is radians per second, not hertz. Whole hertz is how many cycles in a second. Omega naught is how much radians it goes through in a second. Okay, so omega naught here, which is, it's easily identifiable. If you have a sine wave, you just identify the coefficient of t in a function. That's the frequency. Okay, what we are looking for is the output response. Okay, now of course, when you apply sine wave to the system, you will have an initial period, that initial transition period, that rises up and then settles down. But we are interested in what happens to yt when or after system response settles down. Now equation 2 tells you what would happen. okay, or what should happen. Basically, if you have an input RT equal to A times sine omega naught t, where A is the amplitude, omega naught is the angular frequency, then the output response will also be a sine wave, okay, of the same frequency. Okay, so the frequency doesn't change. So you can see here the coefficient of t is the same omega naught, but the amplitude will change. It will be modified by a factor of m. Okay, so it's a times m. Okay, so the amplitude of the output response in steady state is no longer the same as a, but it's some value of a times m. Also, the initial phase angle, that's the second part of inside the bracket of sine wave, that's the initial phase angle phi, would also be different. Okay, so you have to multiply the amplitude by that factor of m. You have to add the additional phase angle inside the bracket for the sine wave. That's sort of a normal rule for steady state response of a sine wave input. Okay, now how do I find the m value? How do I find that phase angle phi? The way you to do it is you use a transfer function. Of course, every system will have different transfer functions. Okay, so you go there, you find your transfer function gs. Okay, of course, there are s's inside of that transfer function, and you replace s. You replace every single s by j. That's imaginary, indicating an imaginary number. Omega naught. Okay, so replace s by j omega naught, where omega naught is the frequency of your input signal or input sine wave. Okay, so once you've done that, because omega naught will be a number, okay, gs is a transfer function with the only variable s. So if we replace every single s with a number j omega naught, you will end up with a complex number. Now, complex number will have a magnitude. Complex number will have a phase angle. Magnitude goes to here. So this is the magnitude of the complex number derived from the transfer function. The phase angle goes here, okay, in equation 2. That is the additional phase you get in the output response out of that complex number. Okay, that's defined in equation 3 and equation 4. So equation 3 says, now I want to work out the magnitude, where if I replace all the s's in the transfer function by j omega naught. And equation 4 says, if I want to find the phase angle phi, then I need to work out the phase angle of that complex number, j omega naught. Now, take a note of that. Every time, if the input is different frequency, if the input of a sine wave gives you a different frequency, then you have to find different m and different phi values. So for every frequency, you will get a set of two values, a magnitude and phase angle. Okay, so these values, m and phi, are very much frequency dependent. Okay, m and phi has nothing to do with other parameters in the input. Okay, so only thing that we care about is the frequency, omega naught. Okay, so once we have a frequency, then we can work out m and phi value. It's quite clear on this diagram, but I'm going to use some examples to show in detail how they work. Okay, so over here, my transfer function is 1 over s plus 2. Okay. If you look at the DC gain, as we discussed before, DC gain in this case is it equate s by 0. So that will give me a DC gain of 1 or 2. So steady state response of output to a unit step will be 50% of the input. So output will be half of the input if the input is a unit step or it's a step signal, whatever that amplitude is. Okay, that's because we replace S by 0. We get half. But frequency response, if my input is a sine wave, then I can't replace S by 0 anymore. What I do is I'm going to replace S by J omega naught. Omega naught is whatever frequency you have for the input signal. So what I'm going to do here is I'm going to assume 3 different input signals. Okay, so R1 equals to 3 sine 5t. That's the first one, and I want to find out the output. R2, I'm changing the input signal, but again, it's still a sine wave. Okay, this time it's 4 sine 10t minus 15 degrees. The third, and I want to find the output response. The third one is 2 times sine 5t plus 6 sine 10t minus 10 degrees. And I want to find out the response. Okay? So we're going to tackle that one by one. First case, R1 equals to 3 sine 5t. Now, if that's your input, you need to identify 3 parameters from that input signal. One is the amplitude, that's a peak value of a sine wave, which is A. It's a number in front of sines. Okay, it's a number in front of the sine symbol. Okay, so 3 here is the amplitude. The second one we want to find is omega naught. That's the frequency of a sine wave, which is the coefficient of time t. So that's 5. The third one is the initial phase angle of a sine wave. Now this is a number normally comes after the t. In this case, we don't have a number come after t. Therefore, the initial phase angle is 0. It's fairly standard. Sometimes people change that format, but that's fairly standard representation of a sine wave. So amplitude times sine, then frequency times t, then plus an initial phase angle. Okay, so you need to identify all 3 parameters. The frequency is essential. The frequency is the one we're going to use first. Omega naught for this input is 5 radians per second. Therefore, I'm going to replace all the s's in the transfer function by j omega naught, in which case it's j5. So 1 over s plus 2 becomes 1 over j omega naught plus 2. Omega naught is 5, so it's 1 over j5 plus 2. Now that's a complex number. Okay, it's a complex number in kind of sort of rectangular form, but it's 1 divided by that. So we need to work out from that complex number, we need to work out the polar form. That means magnitude and phase angle, which is quite straightforward because what you do is this is 1, which is the same as 1 with an angle of 0. This is 2 plus j5. 2 plus j5, the magnitude will be square root 2 square and plus 5 square. The angle will be arctangent 5 over 2. So you work this out, and then you do magnitude divided by magnitude, phase angle 0 minus whatever phase angle you get there. The phase angle at the bottom is actually positive 68.2 degrees. But because it's 0 minus that angle, it becomes negative. Okay, so I'll work out the 2 values here. One is m. That's the magnitude of the transfer function when the frequency is 5. Okay, I have an angle of minus 68.2 degrees. Now the rest is easy, because to find the steady state output response to that particular input is A times M. M is 0.149, so 3 times 0.19. Sine 5t, frequency doesn't change. Okay, so it's the same as the input, sine 5t. And then remaining part is whatever you have the initial phase angle, in which case is 0, plus the phase angle we obtained from the complex number, or from the transfer function. Okay, so it's 0 minus 68.2 degrees. So therefore, if we reorganize that, 3 times 0.19 is 0.57, and sine 5t minus 68.2. That is a steady state response of this system to this particular input. Okay, so the amplitude of the output in steady state will be 0.57, and the frequency is the same, and phase angle is minus 68.2 degrees. That's kind of approach. Okay, so if I change the input a little bit, now this time my input in equation number 2 is 4 times sine 10t minus 15 degrees. The transfer function is the same. But this time, if we identify these 3 parameters from the input, I get amplitude, the number before the sine symbol, the frequency, that's coefficient of t, that's number before the time t, which is 10, and then the initial phase angle, that's minus 15. So I've not written this down because I'll need that later on. Okay, so it's minus 15. Just make a note of that. Now, if you see here, the omega naught is 10. In the previous example, the frequency of the input is 5, but this time it's 10. So the 10, what I need to do is replace all the s's by J10. So 1 over J omega naught plus 2. The process is the same, but number is different. So it's 1 over J10 plus 2, not J5 plus 2 anymore. And I end up with a complex number again. A number divided by 1. This is, you can see, consider that as a complex number. It's just imaginary part of that 1 is 0. Okay, so 2 complex numbers, you divide them, then what you should do first is convert them into polar form both, and then divide the magnitude and subtract the phase angle. And I end up with a magnitude of 0.098 and the phase angle of minus 78.7 degrees. Once you got there, okay, once you get your equation number 5, and you know your m value, you know your phi value, okay? The rest is easy. So you just take the input, look at the amplitude, times that by m that you obtained from GS. Okay, so it's 4 times, no, it's not 3, it's 4 here, okay? 4 times 0.098. Sine, that's the same. 10t, the frequency remains the same. This is the minus 15. That minus 15 comes from the input. So keep it there, okay? You need to copy that down. What you need to add to is the phase angle you work out from transfer function. So you add minus 78.7 into inside the bracket. Okay. Now again, I don't think this will be quite right. It will be 0.3 something, 392 or something. It will be 0.392. So there's a small mistake there. Sine 10t. Combine these two numbers together, that will give you minus 93.7. See? So you can see here, because the frequency of input is different, I have to do all the calculations all over again, because you will have different numbers in the transfer function. Okay, the process is exactly the same, but you have to use the new frequency from the input and work out the magnitude and work out the phase angle from the transfer function. The rest is straightforward. The next example. Now I have R3. Now that's interesting. The R3 is the input of two sine waves. Equation number 2. Now if you look at the first sine wave, amplitude is 2. Phase angle, or initial phase angle, is minus 20 degrees. The frequency is 5. The second part is 6. Amplitude is 6. Frequency is 10. Initial phase angle is minus 10. Now I have two frequencies. Which one am I going to use when I calculate magnitude and phase angle? The answer is we need to use both. Now in my previous two examples, we already worked them out. Okay, so I have, on this slide, I have equation number 5. That is the complex number when the frequency is 5. I'm just being lazy here, see? And you could actually restart over again, but that's the same process because my frequency is the same. Someone can copy that result over. So 0.19 with a degree of minus 68.2. I have also worked out the M and phi value when the input frequency is 10, and then this will give me this value, 0.098 for the magnitude, the phase angle minus 78.7. So I'm going to copy that over as well. So I'll get these two. This one, J5, is for the frequency of 5. J10 is for the frequency of 10. So you're going to apply what you do when you try to work out the output response. You're going to apply the magnitude and the phase angle to the first part. This magnitude and this phase angle to the first part or first term of input. So in this case, because the input frequency is 5, and I know the magnitude of this frequency is 0.19, okay, from the transfer function. So I'm going to multiply the amplitude 2 by 0.19. And then I'm going to copy sine 5t minus 20 down from the input, sine 5t minus 20. Add to the phase angle we worked out for that frequency from the transfer function. So add minus 68.2 there. For the second part, because the frequency is 10, so you need to use equation 5 here. Okay, so I need to work out that, or I need to use the magnitude and phase angle when the frequency is 10, because the input frequency is 10. So this time it's a 6, which is the amplitude of the input, times the magnitude of GS at this frequency, so 6 times 0.098, and then you copy the rest down of the input down, sine 10t minus 10, and then you add the phase angle, you work out from the transfer function, minus 78.7. The overall response, because I have two parts, the overall response is just add them together. We are dealing with linear systems. So one input gives you one output, second input gives you a second output. If you put two inputs together, you can add two outputs together. Okay, so we organize that, 2 times 0.19, that will give me 0.38. Sine 5t, this combined with that, 20 with 68.2, that will give me minus 88.2. Second part, 6 times 0.098, that equals to 0.588. And sine, there's a minus sign left here, so it's sine 10t minus these two numbers together, minus 88.7 here. Okay, that's how you work out the steady state response when you have 2 sine waves of different frequency as your input. And of course, you can have more than that, okay? You can have more than 2, but what you do is that you just deal with them individually, one by one. Different frequencies, you have different magnitude and different phase angles. Therefore, the output response will act differently. Now this we can go a bit further than what the previous example. Now this time I actually use a very simple transfer function, 1 over 1s plus t, where actually I set t to 1. Okay, so it's basically 1 over 1 plus s. And then what I've done here, I actually assume different frequencies. So start from 0 to 0.1 to 1 to 10 to 100. And and then I'll work out for every frequency, I work out the magnitude and the phase angle, which give me this column. So when frequency is 0, it's 1 over with the angle of 0, which is the same as DC gain. When frequency is 0.1, for this particular transfer function, the magnitude is 0.995, the phase angle is minus 5.7. When the frequency equals to 1, the magnitude is 0.707, the phase angle is minus 45. And so on. Now, all that, okay, the magnitude and the phase angle is known as the AC gain. So the whole column is a set of AC gains for this particular transfer function, okay? As opposed to DC gains, because we have AC gains, we have DC gains. AC gains represent the gains at different frequencies. So that's why you have more than one. There will have many, actually, because the frequency can be infinite number of them. And you can have infinite number of AC gains, whereas you can only have one DC gain. That's when the frequency equal to 0, which is the first one here. A DC gain will be a real number, but AC gain typically will have magnitude and phase angle, and they change the output response to a sine wave by modifying both amplitude and initial phase angle. Okay, and note that because my transfer function is 1 over 1 plus s, t is 1, so time constant is 1. Corner frequency is 1 over t is also 1. So you can see here, this 1 is my corner frequency. Okay, at corner frequency, the changes will always be something like 70% of the DC gain. Okay, so DC gain in this case is 1. Then for this particular frequency, at the corner frequency, the magnitude will be 70% or 0.707. The phase angle will always be minus 45 degrees. Okay, that's the corner frequency for you. If I look at them graphically to see what these all means for different frequencies, I have set next one to show you. I have 3 responses here. The first one is that when the frequency is at 0.1, now the red dotted line is my input. The blue line is a steady state output of the system. Now input is obviously a sine wave, and the output is also a sine wave. But if you look at the frequency 0.1, the magnitude is the AC gain of the transfer function. The magnitude is 0.995. So 995 is 99.5% of the input. So that's why you can hardly see much difference here. The phase angle of the AC gain is minus 5.7 degrees. So there's a slight lag. Okay, it is slightly behind the input. When I change the frequency to 1 radians per second, the AC gain would be 0.707 with a phase angle minus 45 degrees. Now you can see the input is here. The output is 45 behind. It's 45 degrees behind. Okay? The peak value is 70% of the input. So the peak value is reduced by 30%. Increase that frequency by another 10, factor of 10. So you can see at 10 radians per second, I have a AC gain of 0.099 or approximately 0.1. That's 10% of the input with a phase angle minus 84 degrees. So you can see the output is roughly sort of 10% of the input, but it's almost 90 degrees behind the input. So this is the effect of the transfer function acting differently to the sine wave of different frequencies. Okay, not only the amplitude will change, but you will get different phase shift as well. Okay, so that's really sort of the essence of the frequency response of a dynamic system if we know the transfer function. So what I'd like you to do is that I'll give you two transfer functions here. I'd like you to do some practices. Okay, find the steady state response of G1, which is this one. And for input R1, R2, R3, and R5. So it's 1, 2, 3, and 5. For the second transfer function, I'd like you to work out the response in steady state for R1, R2, R4, and R6. Okay, good luck.